Hey, it's Mr. Shrum, and welcome back to the Models of the Atom walkthrough tutorial for physical science. And we left off right before this structure of the atom section. So let's get into the actual structure of atoms. And according to modern atomic theory, each atom is made up of three subatomic particles. Subatomic means smaller than the atom, within the atom. We have protons, electrons, and neutrons. Protons are positively charged, so think P positive. Electrons are negatively charged, and neutrons have no charge. They are neutral neutrons. The mass of protons and neutrons are nearly equal. And compared to those guys, electrons have a very small mass, about 1,840th of a proton. So those do not account for the atomic weight, but we'll get into that a bit later. Protons and neutrons are located at the center of the atom, and that is called the nucleus. The nucleus is very small compared to the actual size of the atom. If you imagine the atom to be a baseball field, the nucleus would be the size of a ball. The rest of the atom is empty space in which the electrons move. Since electrons display the behavior of both particles and waves, their position is indicated by an electron density cloud. You can see that here, where in certain models you see them orbiting in very defined lines. This cloud gives it a more realistic depiction of how electrons can move. Where the cloud is darker, it is more likely to find electrons there. But if you move out to this lighter region of the cloud, the chance you find electrons in that area is lower, but you do still find electrons there. Well, because this structure is similar in the atoms of all elements, how can you tell which atoms are from different elements, right? So how can you identify elements from their atoms? Well, the atoms of an element can be identified by their atomic number, and we can determine that by the number of protons in the nucleus of each atom. So for example, a hydrogen atom has a single proton. Here we go. That is hydrogen. Helium, on the other hand, has two protons, right here. So the atomic number of hydrogen is 1 because it has one proton. Helium has two protons, so the atomic number is 2. Although the number of protons in an atom of a particular element is fixed, the number of neutrons is not. For example, hydrogen always has a single proton, but may have 1, 2, or 3 neutrons. Atoms of the same element that have different numbers of neutrons are called isotopes. And these isotopes exist for all the naturally occurring elements. The number of neutrons doesn't affect the chemical properties of an element because these properties are determined entirely by the number of electrons. Protons and neutrons together make up the mass number of an atom, as the mass of electrons is very small in comparison. So a hydrogen isotope that has one proton and one neutron has a mass number of 2. Okay, so hydrogen, the atomic number is 1 because it has one proton, but if it has one proton and one neutron, the mass number is the number of protons and neutrons in the nucleus. So that's why that isotope has a mass number of 2. The isotope with one proton and 2 neutrons has a mass number of 3, and so on. Okay, so be careful about distinguishing the atomic number and the mass number. And this is how things are written in the periodic table. So you will have the element symbol, the chemical symbol, and then you have the atomic number at the bottom and the mass number on top. So sometimes that's written here, like boron, mass number 11, atomic number 5. So for every isotope, the atomic number and mass number are represented with the chemical symbol. By subtracting the atomic number from the mass number, you can find the number of neutrons, the number of neutrons in an atom. In the case of boron, the number of neutrons is 6. So do you understand how that happens? You have the atomic mass number, means protons and neutrons in the nucleus. There are 11 of them. 5 is the atomic number. That means there are 5 protons in the nucleus. And if you subtract 5 from 11, 11 minus 5 equals 6. That means there are 6 neutrons in the nucleus left. Okay, so we're going to try to match the neutrons or the number of neutrons to the correct isotope by studying the atomic number and mass number of each isotope. Drag the items on the left to the correct location on the right. So we have the mass 9, number of protons 4, 9 minus 4 equals 5. That's the number of neutrons there. Then we have 19 minus 9. That'll be 10 neutrons. 20 minus 10. 16 minus 8. 8. 7 minus 3. 4. Okay, let's see how I did. Wow. Nice job, Mr. Shrum. All right, so now we're going to look at atomic orbitals. Orbitals, okay. We know that the path of an electron around the nucleus is described as a cloudy space where the electron is most likely to be found. This space is called an atomic orbital. The number and shape of atomic orbitals depends on the energy sublevel associated with them. The nucleus of an atom is surrounded by multiple shells of energy called principal energy levels. The energy level closest to the nucleus is denoted as n equals 1. And as we go farther from the nucleus, the energy levels are denoted as n equals 2, n equals 3, and n equals 4. And each principal energy level contains one or more sublevels. And the sublevels in a principal energy level are determined by the number used for denoting the principal level. So for example, the principal energy level, n equals 4, has 4 sublevels. Each energy sublevel is associated with one or more orbitals. And we classify those as S, P, D, and F. The lowest principal energy level, n equals 1, has a spherical shaped s orbital in its one single sublevel. So we have that here. And the energy level represented by n equals 2 has one s orbital in the first sublevel and 3 dumbbell-shaped p orbitals in the second sublevel. So that will be these. And then after that, you have n equals 3, that energy level. That has one s orbital in the first sublevel, 3 p orbitals in the second sublevel, and 5 d orbitals in the third sublevel. The first 4 d orbitals are cloverleaf shaped, and the shape of the fifth orbital is more complex. And then n equals 4 has one s orbital, 3 p orbitals, and 5d and 7f. and then all of those shapes for F are really complex. And so this means that as you go up in the energy level, electrons can be found in these higher levels. And this table will kind of show you what's happening. So we have this energy level, first orbital, second energy level, third energy level, fourth energy level. And then we have those P's. And we have the D's. See how those shapes get really complex? And then F. Those are just crazy. So 1s has one orbital, n equals 2, 2s and 2p. We have 4. And a way to do this is just to add it up. 1s equals 1, 2s and 2p, that equals 4. 3s and 3p and 3d, 9. 4s, 4p, 4d, 4f, 16. And we'll look at those questions for the models of the atoms tutorial. But in summary, now we know that if we keep on cutting any object into smaller and smaller pieces, we arrive at the basic unit of the object called the atom. The atom as we know it today includes positively charged protons, negatively charged electrons, and electrically neutral neutrons. The number of protons in an isotope of an element defines its unique atomic number. The protons and neutrons together constitute the mass number of that atomic isotope. The electrons move around the nucleus in an empty space. This space is described as a density cloud that contains the probable location of an electron. And those are called the atomic orbitals. And we classify those as S, P, D, and F, depending on the energy sublevels where those occur. Modern atomic theory is based on the ideas and findings of those pioneers like Democritus, Dalton, Thomson, Rutherford, and Bohr. Their work influenced many modern innovations. And with the knowledge of atomic structure, we now understand the nature of various elements and how they change due to chemical reactions. All right, so we finished the models of the atom. And next, I'll go through the tutorial and point out some key information for questions. And then if you're still having trouble, go ahead and message me in Canvas or email me and I can help you out. But until next time, see ya.